Yeah, I wanted to do a bit more practice on the grammars, but also do like some rigorous examples of the pumping lemma, because you actually have to do those on your homework. So I figured maybe, painful as it is, you might want to do some of those.
You going to start with those?
Well, you want to do those first? Is that your preference? I see. You want pumping lemma, huh? High demand for pumping lemma. All right. So why don't I didn't write it down here, but why don't I write down what the pumping lemma is? Or why doesn't someone help me? Given regular language L, so what does the pumping lemma say? So there exists, or there is, P, which is the pumping length, so this is an exercise in quantifiers, such that I guess I'll put it down here. For all, so I guess, yeah, for all strings S in the language with the length of S bigger than this pumping length, maybe greater, it doesn't matter, greater than or equal to, let's say greater.
So much for the vigorous proof.
No, they're both rigorous.
Okay.
This is a non-deterministic rigorous proof. We could either make it greater than or equal to. Yeah, still rigorous. So what is next? There is I'm getting confused. So there exists a decomposition so I can decompose S equals X, Y, Z with what? So there's a composition of S. I can break down S to three parts. Right, with the first two parts happening before the pumping length. I guess we'll make that greater than or equal to, because that's less than. Otherwise, yeah. Right, with Y non-zero. Oh, man. And I wanted to have this on the board, but I'm writing too big. Maybe, can you see down here if I write down in the gutter here? Yeah? Such that for all j, y is a loop. So x, y to the j, z is in L. So that's the pumping lemma. So this is some property that all regular languages have. That, any really long string is not interesting. It's just some small string, or there's a finite number of strings, and all the other arbitrary long strings you get from pumping up. So that's what that says. So that I can find a pumping length, which is generally the number of states in the machine. It'll always work. Sometimes you could find a pumping length that's less than that, but the number of states in the machine will always work, such that any string bigger than that is just something ratcheted up, from something, something ratcheted up. Okay, so this is hard. One definition of complexity is alternation of quantifiers. I don't know if you've ever studied logic. Actually, we have. One definition of complexity is how many times you have these things switching. Right? It's not. Did we talk about that? No. So this is an aside, because we might do something called alternating Turing machines later. So this could be interesting. So if we have many quantifiers of same kind, these are easy to understand. So if I have, there exists x such that there exists a y, such that there exists a z, such that there exists a w, such that x plus y plus z plus w equals 0, that's an easy statement to understand. I can have as many of those as I like, or for all x, for all y, for all z, for all w, f of x, y, z, w equals 3. These are very simple to understand. It doesn't matter how many for alls there exists I have. They all kind of merge together. But every time I alternate a quantifier, it's like it's like he thought, that I thought, that you thought, that he thought. It's one of those things that alternates a lot. I mean, it gets more and more complex. This is one definition of complexity. And I think someone looked into this. I think it's impossible for humans to understand more than like 4 or 5 quantifier alternations. They're just, they're just really, yeah. They're just like, there's just no chance. Just for us to, somehow our brains don't work that way. So in some sense, maybe that's an argument against this is a right way to encode human thought. Maybe if we can't understand most of the sentences encoded this way, maybe there's a problem with that. But in any case,
But it doesn't matter. We're going forward anyway.
but in any case, this is understandable enough. But it's still hard. This is why calculus is hard too. Have you ever wondered? Limits? No. This is why calculus is hard. So calculus is epsilons and deltas are like that. For all epsilons, there exists a delta such that for all x, right? That's why limits are hard to understand. They're an elementary thing with one quantifier alternation. This is just one quantifier alternation, and already, I guess 2 quantifier alternations. I'm sorry, 2. So
Could you take a regular language and just show how that works?
an example of this for a regular language. All right. Zero star, 1 star. So I claim, well, I'll look at the machine to figure out the pumping length. So I guess I could take P equals,
1 diagonal, 2.
no, 1.
Oh, 1, yeah.
Yeah. Huh. So I think you can actually take,
So this machine can have no zeros also.
Which is fine, but it has to end.
Well, but this machine has to have a 0. But 0 star, 1 star doesn't.
It doesn't have to have a 0, but it does have to have.
It has to have a 1, the way you've written.
No, it doesn't.
It needs
No.
a final state somewhere.
this is the initial state is final.
Yeah, 2 final.
Oh, right.
Oh, is that with the little circle? Oh,
Yeah,
I see.
the initial state is also final. So this will accept the empty string. So here's 0, 0 star, 1 star. So I claim actually the pumping length is 3. So there's 3 states. So actually, why don't we show, I think we could show that the pumping lemma works for 3 and it fails for 2. That might be, if I took pumping length 2 here, this statement wouldn't be true. So for example, let's try it. So P equals,
There just has to be a P.
they're just, I mean, I don't have to find it exactly. I could take any P greater than or equal to 3. Will work. So P equals 3 here. So let's see. So if I take any string in L. For example, let's just so I need to find a decomposition. I just need to find 1. So I need to decompose S equals x, y, z such that the length of x, y is less than 3? All right. I should check the numbers in the book. Does anyone have the book with them? I don't know if it's less than.
Less than or equal.
It's
Greater
less than or equal?
start.
Is that how the book does it? Yeah. It doesn't really matter because p is not really fixed, but I want to stick with the book. Less than or equal to. Just for consistency's sake. All right, so such that xy is less than or equal to 3. Find a decomposition such that xy is less than or equal to 3, such that xy to the j z in L for all. I guess it holds for 2 also. Huh. Oh, this one's too easy. Why don't I take make this 1101 star? I apologize for the change. So 1101 star. Okay, that'll be more interesting. I claim actually. So the pumping length here is 5, I guess, automatically. I claim actually I could still use 3. 3 will still work here. Yeah, 3 will still work here. So let's take something in this language. But 2 won't. Okay. So pumping length, the number of states of the machines will always work, but you could take less. 0, 0. Okay, so now just keep in mind, this is completely irrelevant to what you're doing in the sense of you'd never actually do this. Never verify that the pumping lemma holds for a regular language, because we proved that in full generality, or the book did. Really? Okay. All right. But in any case, you never really do it this way. So this is not like learning a practical technique. It's just, let's get a feel for this, for this pumping lemma. So basically, I want to show that I can always find a string of length less than or equal to 3 with the y non-zero so that everything's in the language. Is that possible? Yes. I can let. So I just need to find 1. Not all decompositions will work. So I could let, say, so it's weird notation. Let x be that, y be 0, and z all this stuff. Okay. Then, let's see. The length of xy equals 3, which is certainly less than or equal to 3. The length of y equals 1, which is certainly greater than 0. So that's true. And what is x, y, j, z? So that's just going to be 1, 1, 0, j times 0, 0, 1. Is this in the language? Yes. So this is one reason, just because the pumping lemma, well, notice, let me back up. The pumping lemma holds here, but just because it holds doesn't mean that much for the language. It doesn't say that much about the language. That's why the pumping lemma holding doesn't prove it's regular. Because all we have to do is find, one decomposition, for every string. So there's still a lot of leeway there. There's a lot of leeway. But the pumping lemma failing is the interesting part. Okay. I want to keep that stuff there. I want to show you why p equals 2 doesn't work. Want to do that? Yep. So what happens when we try and take p equals 2 here? Let's try p equals 2. What's that?
We would be pumping on the 1. Is xy.
So we have to. we don't have any choice then, right? Then, so what are our, so what are our choices? There's only two possibilities here. What are the two possibilities for the decomposition?
Y is x is 1, y is 1.
So because we have that xy is less than or equal to 2 here, and y greater than or equal to 0, that restricts our decomposition, right? So if I take this string, xy has to be in here, has to be less than or equal to 2, right? And y has to be non-zero. So this is one possible decomposition. What's the other one?
X is 0 and y is 2.
Right, so x is nothing. Nothing for x. That's okay. That's allowed. Y is 1.
What would have to be 1, 1?
It could be 1 or 1.
Actually, I guess there's three possibilities, yeah. So y could be 1, 1, and z could be all this stuff. So make that 3. Or x is nothing, y is just 1, and z is all this stuff. So what's wrong with this? Why does this language not have a pumping length of 2? What happens in all these decompositions? What's violated?
No longer matches the language.
Create strings in the language.
Right. So this is bad because x to the j, sorry, x, y, j, z is equal to 1, 1 to the j, 0, 0, 1. And this is not in the language because I can only have 2 1s at the beginning of the language. Right? So that would be an invalid decomposition for this thing. What about this? X, y to the j, z here is 1, 1 j times. That's also invalid, right? And same for here. So this is bad. Why is this not in the language? Because the language can only have 2 initial ones. The star only applies to that.
So the 0 can just drop out and you can have a whole bunch of 1s.
Yeah, but if you have any zeros.
But there has to be,
With this particular string.
You chose the string ahead.
yeah.
You can choose the string.
This string is not in the language. So I can choose a particularly difficult string. And this string is, if I pump up j, this has to hold for all values of j. So it doesn't work. And this is bad also, right? Because it's 1 to the j, 1, 0, 0, 0, 1. So this is not in L either. So they're all not in L. All right. Good old pumping lemma. Huh?
Just P2 fails, and when you're trying to prove one that's irregular, how do you know that?
So you have to prove it for every possible p. So even if something, like, even if the pumping lemma fails for 2, it could work for 3, right? So this is the hard part. To prove that the pumping lemma fails, you have to prove it for every conceivable choice of p. So it seems like an infinite amount of work. So that actually leads right into our next topic.
It's not that it fails. To prove that it fails, you have to...
To prove that it fails, you have to prove that it fails for every possible p. And let's do that by logic. Let's negate this. What happens?
So here, even if one condition passed, the pumping lemma holds.
So even if I could find just one of these things, that's good enough. You just have to find you have to do this for every string I could give you. Okay? That's why there's many levels of alternation here. So you have to find one. So you have to find one p such that for any string someone could give you, you can find at least one example where this is true.
Okay,
So that's why it said there exists for all there exists.
so that 2 exists.
Yeah. So for any string I could give you, you have to find at least one of these. So in this case, it fails because I find one string where it doesn't work. I could find other strings where it does work, but that doesn't matter.
So to prove a language that's irregular using this, you got to do it for every language.
Right. So let's do that. So the negation. What's the negation? So do you guys remember how to negate quantifiers? you reverse them. So whenever you push a not through a quantifier, it changes it from an exists to a for all. So not there exists equals for all not, and not for all equals there exists not. So when you push a not through a quantifier, it changes its type. So what's the negation? So for all, I'll call it putative pumping length. For all putative pumping lengths P, there is, so I just have to find now one example. So there is an S in the language with the length of S greater than or equal to P, such that what? So for all
decompositions.
So for all decompositions, so this is a good exercise in just logical thinking. For all decompositions, S equals X, Y, Z with X, Y less than or equal to P, Y greater than 0. Yeah, I guess there's 3 qualifier onto. Yeah. So this is really a for all J here. I forgot about that. There's 3 quantifier alternations, so that there exists a J such that X, Y to the J, Z is not in L. Whew. So that's why this is hard. 3 quantifier alternations. So we're approaching the limits of comprehensibility.
For this generation. Next generation will be able to do it.
Yeah, they'll have better methods and higher comprehension abilities. Okay. So that's a mouthful. So do you want to apply that? Do you guys want to try and apply that to something or no?
We'd like to watch you do it.
Aha. All right. So which one should I do? Have we actually ever done this? I don't know. I haven't done this. Should I do one of these or no?
Yeah.
Yeah. So but you just need some review. Okay. Yeah, it is kind of a weird thing. So.
But he seems to play an adversarial game where he asks the adversary for more information than is strictly available. The number of states and the length of the loop.
All right.
Well, the number of states is what gives you the pumping rate. And
So I'm going to think of some examples. Did you do palindromes? Is not regular?
Yeah.
So you did palindromes. Did you do WW? Is not regular?
No.
No?
WW is not regular, but that's in the book.
Oh. All right. So we're going to do.
WW is the exercise. WW is the example.
I guess we'll do this. There's a couple of examples. So basically, there's examples where you need arbitrary amounts of information communicating to 2 parts of the string. There's other examples where the length of the strings grows greater than linearly. Right? So the strings in the language, let's say if you do strings of length n squared or n cubed, then this pumping lemma can only, grow things linearly. So that won't work. So those are 2 types of problems you could do. So we could do one of those nonlinear ones. So this is number 7. So L equals 0 to the 2 to the n. I guess I called it x there. N greater than or equal to 0. So this is, I guess it starts with 0, 0, 0, 0, 0, 0. If you're bored, you can come up with a context-free grammar for this. But what do you think? Is this regular? No. All right, so not regular. So who's going to walk me through the proof? So how do we do for all p? 0 to the 2 to the n?
Yeah.
It's always 0, right?
Using the 2 to the n using regular mathematical exponent, and 0 to whatever that is.
All right.
Meaning
So why don't we call it 0 to the m? M equals 2 to the k. K greater than or equals 0. You like?
sure.
All right. All right, so how do we do these proofs? So-
pumping length P.
So pick any pumping length P, putative pumping length. Doesn't matter.
Choose a good string.
So I have to pick a string.
All right.
So what string do you want to pick?
How about 0 to the P?
Or
0 to the P. 0 to the P.
So for these things that are like the gap is nonlinear, so we have 0, 0, 0, 0, 0, 0. You know, gap gets big. So what's the idea? You want to pick one of these such that the next guy in the language is more than the pumping length away. And then that will give us the violation. So what you have to do, so side calculation, is figure out what the gap is. So what's the length of the gap? What's that? Minus 1, plus 1? Let's see. So what's the length of the gap here? So it goes from, so there's a 0, which is 2 to the k long, and this one is 2 to the k plus 1 long, right? So how far apart are they?
2k plus 1.
What's the distance here? This is one of those problems you learned in elementary school, sort of. Subtraction. So I'm sorry, I'm being facetious here. Let's see. 2 to the k plus 1 minus 2 to the k. What's that? That's because this is twice 2 to the k, so this is just 2 to the k, right? Okay, so the gap is 2 to the k. So we just want to make sure that 2 to the k is greater than p, right? And then we'll be fine. The pumping length won't be able to jump to the next thing. So I guess I could take log base 2 to the p, but let's just take k equals p. So what's s? S will just be a string of length 2 to the p. Then what? So that's my there exist. Now, so pick any decomposition so this is 2 to the p long. You pick a decomposition x, y, z. So this is any arbitrary decomposition with x, y less than or equal to p and y non-zero. Then what? So what do I have to do now? So do I have to do that for all j? No. I just have to show there exists a j. I just have to show there's one case whatever decomposition I pick here, I just have to find one case when I ratchet it up, something that's not in the language. All right. So here's 0 to the 2 to the p. 0 to the 2 to the p plus 1. So what can I consider? What string will not be in a language now? What's the easiest example I could take?
X, Y, Y, Z. J equals 2.
Yeah, j equals 2. X, Y, Y, Z. So someone tell me why this is not a language. Who hasn't said anything? Actually, I'll grab my Coke, and you guys think about it. So there are ideas, right? Like, so sometimes there's things you learn that are conceptual ideas, and there's nuts and bolts. This is nuts and bolts, right? This is the stuff you send the technician in to do. But, so this is probably one of the more technical things you have to do in this class. So you can think of it as interesting or horrible. I don't know. So who's going to tell me? What's wrong with this string? So this is x, y squared z.
Well, you need an extra 2p zeros to make it to the other side, and y is between 1 and p.
You can never get 2p zeros.
Right. So y is length 1 between length 1 and p, right? So where in this graph could it lie? Or when this on this line? Well, actually, not even halfway. So like y must be, x y squared z is in here. Right? It has to be somewhere in here. Right? Because this is length p. Right? And this thing is length 2 to the p. We chose it that way. All right? And so this is in L. In L. This is in L. All this stuff in between, all this stuff is not in L. Everything in between. So the length of y is greater than 0 and less than or equal to p. So y can't be in L. All right, so not completely rigorous. Oh, sorry, xy squared z. Can't be in L because it just can't make it. It needs to get to the next outpost, L outpost, it needs to go 2 to the p steps, but it can only go p steps. So this is the proof for all these things when, instead of 2 to the k, you have n factorial, or you have n cubed, or any nonlinear gap. If the entries in your language spread out greater than linearly, there's no hope. You'll never be able to get it, with a regular language, because it can only churn out things in a linear fashion just by looping around. So all those proofs are the same. You could change it to n cubed, n to the 4th, n factorial, anything you like. And all you have to do is compute the difference between any two subsequent members and just wait till it gets big enough, bigger than your pumping length. And that's it. There's no way you can,
The converse doesn't necessarily hold, though. You can have the number of zeros, each additional string in the language has fewer additional zeros, like a logarithmic decay kind of thing. That might be able to be done.
You're saying, can you have a regular language with a logarithmic decay?
That's probably where we'd want to
No.
put it down.
Well, so you have,
So they pump down.
so you can pump down.
Well, I'm not sure what the question is. Can you have regular languages with weird properties, or can you have non-regular languages that don't behave like this? What's your question?
Well, I'm thinking that, well, the string I'm thinking of, say it's, instead of 0 to the 2 to the k, it's 0 to the log of k, or something.
Where the gap is getting smaller.
Yes.
That will be, well, that will actually be regular. That's
Yeah,
we can
that's what I
talk
was
about
thinking,
because
you'll eventually get to a point where it's just going to be one.
yeah, but that's kind of we can talk about that after class. That's an interesting problem, but I don't think it's really well formed. You know, the way it's phrased. Like we're in discrete land, so things can't get arbitrarily close. So never you mind. That's not important.
So if you have regular spacing, then you can just get back to that state, so it's already going.
Probably, yeah. I mean, if it's a regular language, you want to give a machine for it. That's how you prove it. You know, but you could have things with regular spacing. You could take, like, say, the even numbers, and then take out random. You know, like the even numbers are a regular language, even lengths. But then let's say I had like a gnome that came by and randomly removed elements from a regular language infinitely many times. Maybe, yeah, you could still have even spacing with occasional like random things being taken out infinitely often. That wouldn't be regular. So there's all sorts of weird things you can do.
Have a rich life, don't you?
Yeah.
Gnomes come by.
Take
away your stuff.
Yeah. Yeah. That's the rich tradition of mathematics right there. The myth of the gnomes. Yeah. All right.
Come up with things like Chomsky normal.
What?
Make that your dissertation.
Maybe Chomsky's a gnome.
Yeah. Yeah. All right. So the other type of example, there's the length examples. What were the other
What's his
ones?
name?
The ones where...
Noam Chomsky?
No.
Sorry, there's humor going on here. Please, desperately try to.
Yeah. Wait, I forgot what the other type of irregular language was. Does anyone remember?
The other type of what?
There were lengths. There were, the gap gets really big. What were the other types?
Where you would think.
Oh yeah, when you have to palindromes or 1 to the n, where you have infinite information, arbitrary large amounts of information being stored. Okay, and those are a little different, the proof style, but I don't know. I think this is enough for now, unless you guys object. Yeah, we can talk about it. We can have more later, because I think there's only so much pumping lemma you can do. Before.
The whole point.
Yeah. All right. If you want to see how that works, try and prove something like yourself. Right now, if you want to try and prove that the palindromes aren't regular using the pumping lemma, and I'll come around and check. All right. So back to grammars. All right. So I guess we'll have a warm up first, just to get you guys back in gear. Do number 2 from today's handout. It's generating a grammar. Good practice. See if you remember your retention rate.
Are we in context free or left right or?
Well, do context free. Do context free if you can, or even regular grammar if you can. Whatever you like. It doesn't matter. Yeah, do context free. It's easier. What's the answer? For 0 star 1 0 1 star.
S points to 0x.
Actually, wait. We'll save yours. I'll give you my lame one first, which is not a regular. Well, it doesn't look like a regular grammar. So I said, I'll go to A1B, and then A goes to, what would A go to? 0A or epsilon. B goes to 0B or 1A or 1B or epsilon, right? So that's everything star, and that's 0 star. But I like Tom's better. Tom has a better answer, I think, because it's regular grammar. So go ahead. What did you say?
So S points to 0S
0S
or 1A.
or 1a,
And then A points to 0A or 1A
or 1a,
or epsilon.
or epsilon. Pretty snazzy, huh? I like that. Does the same thing.
And that one on the right is regular, and the one on the left is context?
Well, I mean, they're both regular grammars, I guess. It's just not in the,
It's context free versus right.
Okay.
yeah.
Well,
They-
they're both context free.
Yeah, they're both,
It's just labeling.
I mean, they both generate they both generate the same regular expression. It's just that it doesn't look, it's not apparently clear here that this generates.
I don't think, does Tom's work there? Because if you go from S to 1A, you don't need a 0.
Yeah, zero.
You don't need the 0. Right, so you get an arbitrary number of zeros, and then you get a 1. So this is kind of cool, because this is how you control, you have a loop, and this is the control letter that gets you out of the loop. So you can even do stuff like, let's say you want to do a loop for a while, then do some stuff, and then start another loop. You can do that with this stuff. You know, you can do this loop, have this A as the exit from the loop. When you exit the loop, you can make a pattern, and then you can get into another loop. So it's kind of getting like to be like programming.
You can do the same thing on the left. The epsilon could be 1, and then S could just be AB.
You're saying the epsilon here could be 1?
Right.
Yeah.
And then it's just AB.
So here's, yeah, so many ways to do it. S goes to AB. That's a clever thing too. Your epsilon, your exit condition doesn't have to be epsilon. It could be 1. So here's another answer. So many answers.
Yeah, epsilon would be.
Yeah, you're allowed nothing after
Oh,
1.
you are so right. My apologies. Yeah, so we only want 1, 1 when we exit out of the 0 loop, the 0 start loop. Then we get dumping out a 1 is our exit condition. Wait a sec. No, that doesn't work. Let's see. Oh, I guess it does. Yeah.
There's no requirement to have a 0. So.
So this says, okay, I have, instead of doing it, oh yeah, I have 2 subproblems. This subproblem is 0 star and ends with a 1, and this subproblem is just arbitrary stuff.
Is that one like either right linear or left linear grammar? The one on the S goes to 0, S, 1A?
Tom's.
That's left linear grammar.
Or right linear grammar? Depending on how you define it. Yeah.
Wait, how,
Well, left linear and right linear, it's kind of an arbitrary distinction of what you call left.
so what does Shai use? Whatever Shai uses,
You
we'll
said
use.
it's kind of arbitrary.
He said some books say it one way and some books say it the other way. So I think he called
The
that
point being that it's a
left
linear grammar.
Depends what you're looking at, right?
This is a concept.
Depends what side of, it's a half empty or half full.
The point
Yeah,
being
what's
it's
on the
linear
left?
grammar rather
It's
than a context.
the non-terminal or the terminal. All right. Well, it doesn't matter, I guess. He's right. All right, so let's do some more interesting grammars from last time. I think we stopped. Where did we stop? Does everyone have the thing from last time?
We did 6, and we talked about 7.
Ah.
We didn't do 8.
All right, there's some interesting ones. 8, we're going to have to skip over for now. Let's see. I think I can dig up the this sucker.
I think we've got a solution for it if you want.
You got a solution for 8? Well, we'll talk about that after. Just wow, there's a property of Ars Digita Corporation on this thing. Those guys are thorough.
Have you checked your back recently?
Yeah.
I saw one tattooed on Shai's.
Yeah.
He's had an expiration date though.
All right. So where did we get to?
We did 7. We talked about 7.
Equal number of zeros and ones, or
Right. We talked about
we did how to do ors, right? Ors are really easy. Oring 2 grammars, right?
8. So.
All right. We'll start with 9. Let's just start with 9. More practice, and I'll dig it up here for those who don't have it.
So we've got to change that and change the whole page on that.
Oh.
It's just scary. You need a //
Oh, thank you. It's hard to type and stand up at the same time.
Yeah.
Oh, that's not it.
Is that how it comes out of the box?
Yeah, I got the surly version. AOL server surly. Was this it? Yeah. All right, so can you guys see that?
You make it, yeah.
All right. You know what?
You can pump it up in
I just like Opera.
the fastest browser.
With a million home pages.
That is the fastest browser on Earth.
How's that? There we go.
It's out of control.
All right. Wow. Well, look at the time. It's already, time is flying. Okay. So why don't we just go plow through some of these together. Some of these are tough. So, all right, so what about the grammar for 0 to the m, 1 to the n greater than or equal to m, greater than or equal to 0? So there's at least as many 1s as zeros. How would I do that? So this doesn't really fall under the title complements, like it says there. But it is building up to it. Okay, so how do you do this one? So this is 9. Okay, Dimitri, this is great. Just for Joe.
Well, you can either add just a 1, or you add a 0 and a 1.
So you're saying, so we could go S goes to S1, or 0S1,
And empty also.
or epsilon. Yeah, that's pretty good. All right, that wasn't so hard. A little warm up. Wait. What about the rest of the class? Are you happy with that? Or no? So I'm adding equal number. I mean, at least as if this were m equals n, then it would just be that, right? 0s1.
Could you also have 1s0?
1s0? No, because all the 1s are after the zeros.
Okay.
So if it was just 0 to the m, remember 0 to the m, 1 to the n was just s goes to 0s1 epsilon. So if we do that, we get this. Oh, by the way, so what if we had, this is not on there, but I guess it's symmetrical. What if m was greater than or equal to n, greater than or equal to 0? So S0, 0S1, epsilon? 0S. Right, because the zeros have to come before the ones. All right. And the other one was, all right, slight variations on this. Maybe I'm beating this dead. But what if n is strictly greater than m?
Yeah, start with 1, 1, and then
You just change
Your
epsilon to 1
epsilon
out
would be
there.
a 1.
It should work.
So yeah, so you have to start with at least 1, 1. Or you could end with at least 1, 1. Either way will work, right? So yeah, the easiest thing is just to do something like this, 0s1, and just make your base case 1. And then you're guaranteed to have at least 1, 1. Right? So you have, because that's what this says. This says that n, there's at least 1, 1 in the picture. Or, well, it forces that.
Smallest string.
It forces at least 1, 1.
But it doesn't have an epsilon to terminate it.
Right, it has a 1 to terminate it. A terminal can be any character. It doesn't have to be an epsilon. And this this forces there to be at least one more 1. All right? So, all right, we're almost done, I swear. So what's the next one? I want to generate the complement of 0 star 1 star. So what about 0 star 1 star? How would I give a grammar that generates that complement?
Something that has, it's got to have a 1 before the zeros.
Okay. I propose a way that involves no brain power at all. How could you do this with limited brain power?
Let you do it.
Well, I'm not going to be there on the test, when you're taking the test, Kevin. So you have to figure out another low brain power way. Let's see. Other low brain power, or less brain power way is to make a finite state machine for it.
Yeah, that's not low, but
I don't know.
it takes a while. It's mechanical.
Really?
Well, not that one.
All right, let's see. I think that's easy for me.
And then you condense it.
If I can do it, come
1,
on.
2, 3, 4 lines.
So what's 0 star 1 star? It's just 0. We just did that, actually. I had a reason for putting this up before.
I mean, it's not bad.
Well, just think in terms of the tools you already have. So here's 0 star 1 star. So what's its complement?
Here's the final state.
The final state.
Right, so here's 0 star 1 star complement. So this is 0 star 1 star complement. So what's the grammar? Someone give me a grammar. A goes to
0A.
right, so this is A, B, C. Right, so A will go on a 0, it goes back to A. Or it could go to B on a 1. B goes to 1B or 0C. And what does C go to? 1C or epsilon. Right, so there you go. That's not so bad. Right. Yeah. It's better to, you could be creative and think about it too.
How about this? S goes to A10A.
C. S goes to A
10A.
10A.
And then A goes to, well, actually, we go to, if you make it C. S goes to C10C. It's the same then. It's the same C from above.
But this doesn't accept the empty.
Well, empty isn't accepted.
Oh, 0 star 1 star. I'm sorry.
C10C would be what it would.
C10C.
Does that do?
I don't know. But see, there you have to scratch your head for a while and prove to yourself that works. Proving grammars work is, I don't know. It seems tough. It seems tough to me.
But in this case,
Maybe that works. I don't know, but I have to think about it. It's probably right. But I'd really...
any string that has a 1 followed by a 0. Right?
I guess. Yeah, I guess that sounds right. And then C is anything? All right, that's probably better. Okay. But I don't know why, I'm still not convinced that that's it. I guess this is an easy example. But the point I was trying to make is sometimes it's easier to convince yourself that a finite state machine does something.
But when you get to 12, you can't do that because 12, you can't make a finite state machine.
For 12.
It's not a regular
Yeah.
language.
But,
It's
aha!
better.
12 is the buildup. So here's one way you can do this. So what is 0 to the n 1 to the n complement. What is that equal to? So this is 12. So I claim you can break it down in terms of the examples we just did. So complements are sometimes really hard to do. They're not trivial, like for grammars, like they are for DFAs. For DFAs, you just toggle things. For languages, you have to do work to get complements. They're generally not easy. So maybe I'll leave you with that. Why don't you think about it for a few seconds? And then also think about 13, the challenging problem. It's not as challenging as I thought. Can you generate a grammar for something that's not a palindrome? So think about that one later in the privacy of your own home. We'll talk about it tomorrow. But, okay, yeah, so closing words. Can anyone tell me a way to do 12 using the other things?
Yes, but
Is it 0 to the m, 1 to the n, where they're not equal, union, the complement we just did?
Right. So if you break it up even more, so this is n greater than m greater than or equal to 0, union. So when can something not be of this form? Either it's not in 0 star or 1 star. So it's not in 0 star or 1 star. If it is in 0 star or 1 star, how could it fail to be of the form 0 to the n, 1 to the n? It could either have more 1s than 0s or more 0s than 1s. So if we call, so it'll be something of the form S goes to S1 or S2 or S3, right? Where S1 generates this grammar, S2 generates that grammar, and S3 generates that one.
So it's ordering three things.
Yeah. So if we can OR things together, if we can take something and OR them together, then we can do something. So let me just write it down real quick. So it's S1 goes to S11 or 0, S11 or 1. S2 goes to S0, S2 or 0, S21 or 0. And S3 goes to whatever, one of those things. All right.
Which one does it go to?
All right, so let's say, well,
This group?
let's call both of these S3. I guess this works. I'm still confused about that one. All right, so anyways, that's enough. That's enough for today.